Alright, so we're gonna get into chapter 4. So that's your first chapter for your rigid body motion. And of course, we will get into the kinematics, before anything else. So the very first thing that you have to know is what is a rigid body. It's just a body, object, you can call it, everything that we have in the world. I already told you that we only categorize into two. One is a particle and the other one is a rigid body. And of course, for a rigid body, you have a non-deformable body, meaning like you can't deform it, and it has a mass and then it has a size. Of course, you truly need to understand this non-deformable body. Okay, that is because you might think like everything in the world is deformable because almost all the objects are subjected to the environment, right? So it's kind of not consistent, this word is. But for dynamics, right, in this scope of study, we take the rigid body as something that doesn't change the shape, when forces act on it. And that force, of course, has a limit. That's why it is. That's why the rigid bodies are non-deformable, because again, there's a limit of the scope of study. You can say like, oh, if I burn a something, is just gonna be deformed, right? You might think that way, but again, that's because we are in dynamics, mechanics, and in this scope of study, we're going to concentrate on forces, and this rigid body is defined. These forces cannot change this body, and that's why we call it rigid body. So there is a limitation of this define of force in the scope of mechanics, dynamic, and don't forget that, So I would say like, so what is the limitation of this force is the non-artificial natural forces, okay? Cannot be able to, deform the naturally existing rigid body, okay? Some of them are actually artificial, what man-made, but of course we're talking about the limitation of that forces, mostly what we have in our environment, okay? And now we will get into trying to understand this non-deformable. Another one is like the distance, the distance between 2 points, okay, on that body is going to be about the same, meaning like it can't be deformed. So if I chose like from here to here, and since we can de-shape the body, that distance will be the same, If you go like, you pick another 2 points, I'm going to pick from here to here, and then you measure that distance of this rigid body, that won't change, okay? So that's what we're trying to say. Again, very, very, short sentence, but every word has a deep meaning, and you've got to use your brain to think with it. So every word, don't just read it, you got to think. What does it say? What does it mean? Okay, go all the way to the real meaning of it. So let's try to give you an example. We have a lot of rulers, right, in the classroom. So if you look at the ruler, that's a rigid body, definitely not a particle. It has a mass and a distinct size. So that ruler, okay, it can move without bending, meaning it isn't elastic, so meaning like this rigid body, the ruler, cannot be deformed, right, by natural forces, or natural forces mean the force you apply to that, okay, to that object. Use your hand and then pull it, it won't do anything. And then of course the rubber band, if you have like a little rubber band, to a hair band, or like anything that you use to tie to something, right? That rubber band is elastic because when you apply a force, and pull it, it's going to stretch, So therefore, the rubber band is not a rigid body because when you apply a force, it will definitely deform. But the ruler, something like ruler, your computer, if you apply a force and pull it or push it, it's not going to change the shape. Of course, if you just throw it or drop it or break it with real, like very very strong one, it might break. However, it might break it, but it is not going to the form, the overall form or shape. It's not going to yeah it can't be deformed, meaning like even though it's broken, you can put it back together and it will still maintain that size and shape. Okay. All right, so again, don't forget the limitation of the force, right? If you put it on the fire, that kind of force is not acceptable. Yeah, we're talking about the mechanical force. All right. So anyways, a planar motion, mechanical force up to certain points. So planar motion, all parts of the rigid body move in a parallel plane. So since it is a parallel plane, we're still in the 2D, two-dimensional motion. So planar motion. So with the motion, all parts on that rigid body. Let's just draw a rigid body. Okay, it's gonna move in a parallel plane. Yeah. So that means this object is gonna stay flat and does not tilt or move in three-dimensional way. Okay. So if I had to draw a three-dimensional axis, instead of rotating, this is moving only on the two-dimensional, so it will just stay flat on that plane. Okay, since it's a 2D, we can describe it like it is on a plane or parallel plane, and it's not going to tilt. It's not going to tilt, or it's not going to move like in the 3D space. Okay, because it's flat on a plane. All right, example is like you take a book, right? You have a book or many books on your desk, and take a book and slide it on your table, and that book is going to move on that table plane. Yeah. If you toss that book into the 3D space, your room, and directly into your room, it will definitely flip, and flip, rotate, and then bounce on, and then land on your floor, floor of the room. But if you just slide on a desk, because your surface of the surface of your desk is a 2D plane, it will definitely slide on it. It won't toss out or flip around like in the 3D space. Okay, so make sure you understand what is a 2D motion and what is a 3D motion in the 3D space. 2D motion on a 2D plane are very important. So make sure you understand three-dimensional, two-dimensional spaces and planes. Okay. Now, of course, we're in rigid body motion, so let's review your particle motion. Yeah. So you have to understand the particle motion and the rigid body motion. They're very different. So if you think about the particle motion, they only translate particles. They only translate. Okay. And particle is a very tiny little, small object, and it is going to move in a straight line. Don't forget the straight line. So therefore, we call that type of particle motion a translation. Like your dust particle, are very very small, floating in the air, but it's not going to rotate. It looks like a little tiny particle. If you look into your room, you're going to see gazillion or billions and billions of particles in the sun rays. So these particles, their movement is only translational, meaning like their motion is only translation. They're moving in a straight line. It doesn't really rotate and like the rigid body motion. So when you think about the rigid body, it goes on a straight line like translate. It also rotates. Okay. So rigid body can translate, it can rotate. Rigid body may translate, may rotate. Okay, it can do, and that's a difference, differences between the particle motion and the rigid body motion. So let's pick a rigid body like a car tire rolling on the road. Is going to move forward and is going to spin. So if the car, I can draw a car. I'm just going to draw a wheel part of the car. So that thing here is your wheel tire. And it can go rotation like that, And also it is going two different motions happening on the wheel, yeah, rotating and moving on a straight line, yeah. So you're seeing two types of motion, translation and the rotation happening at the same time when you drive a car. Those motions are happening on the tires, all four tires of your car at the same time, and there you are sitting in your car. Okay, so anyways, again, motion is very, very complex because many things move. Yeah, the car is moving, you are moving with it, and the earth, right, that car is on is also moving. The entire planet, the galaxy is moving. The stuff inside of your body is also moving, and the stuff inside of the car is as well moving at the same time. So it's a very, very complex one, yeah. And that's the reason why we have to ignore, so many motions and concentrate only one or two motions, even though it is too complex to calculate on a paper, yeah. So for now, go all the way to the very, very simple, basic particle translate straight line, yeah. Rigid body rotate and then translate, okay. So that's all you need to know at this level. And then we're gonna break it down, this rigid body motion, yeah. The very first one is we give it like just a translation, I mean just go in straight line, yeah. My drawing is no good, so anyways, just go a translation motion, we call it pure, yeah. Just translation, no rotation. Pure rotation is just rotation, and every time something is rotating, there is, all right, a distinct or a fixed axis, yeah, axis. So you have a x. I hate this thing to draw. Axis. Okay, so rotation. There is a fixed axis, and we call it pure rotation that the rigid body can do. And then we have something called the GPM, is your general planar motion. So this one is both of that, yeah. So we have a translation and rotation in this type of motion. So you got a pure translation, pure rotation, and rotation and translation, we call it the GPM, which is general planar motion. Or some people love to call it just a planar motion. Okay, so if you think about the translation, I already gave you a lot of example on translation. I can give you one more. Yeah, a train moving straight on a track. Yeah, train on a track moving straight. So that's a translation. Rotation. You have a ceiling fan. Yeah, at your home. So in your room, see the fan spinning, and that's rotation or pure rotation. Then a combination of your translation and the rotation. Yeah. Most of the real world objects are that way. I already told you so many examples of them. So example is the previous, yeah, example, your rolling car tires, it moves forward and also it spins. So make sure you know these three, different types of rigid body motion. If we have to go very, very deep, if you think about the translation, there's no rotation, and every point on a body, on that rigid body, is going to move in the same direction. I also told you 1,000 times, every body is made of tiny little stuff, and they're just staying there with a attractive force together, aggregate structures. For a human, your structure is being built every second of the time with the food that you're putting into your body. If you don't put food into your body or water, it will wither. Meaning like, because you're not giving the system, your body system, what it needs to build that shape or structure that you have. So your food is kind of like a fuel to the structure that your body DNA gotta build every second of the time, to maintain that form. So as you age, the system got very, very tired. It can't be able to build it in the way it was doing before. So when your system was fresh, like you were born and then you grew up, right? Your body system is very efficient in using the food fuel to make make it every day the same form, right? As we do this activity again and again every day for some time, your system get very tired, and it can't be able to maintain that shape when it makes it anymore, and worn out. So anyway, so the same as that, every point on the body, doesn't matter what rigid body you pick, a ruler, a train, a car, and the things that made, right, the little things that made that. So I could say like the chemical elements, bonded with the physics forces, and we can see each point on the body is also moving in the same direction. Okay, so even though we define the pure translation as the resultant force, resultant force going straight, and the direction of that translation, we will say like just a straight line of that rigid body. You gotta understand that that rigid body is made up of billions and billions and billions of little tiny thin particles in there, and if we take a point on that rigid body, that point also go in a straight line. So you will have a billions of straight lines, making a resultant straight line going forward in translation. So that's a deep meaning of the motion. And as a pure rotation, the same thing. Your body is going to spin around a fixed point on this axis. You always have an axis to make a rotation. So then if we go down all the way to the points, little tiny points, to refer to the ingredients or the composition of the rigid body, these points are going to move at different speed depending on the distance from the center, which is a little bit different from this. So if you take let's say a rigid body here, and that body is rotating, okay, now we go all the way down to the little tiny point on that body, and you're going to pick a point, and this point, all right, also move. That point also move with the body. So different points move, but each point, okay, on that body is going to move with different speed, by the way, different speed. And that speed depends on the distance, right, from that center of axis. Okay, so how weird that is, so different points move at a different speed depending on their distance from the center, from here axis. So that's very important point. If you want to get a Nobel Prize or whatever. Of course, nowadays people don't respect education, but education is actually really important. Not to make money. It just the whole thing that is going on in this world is just to me is amazing. To me, I always want to know what's going on. I really truly want to know and try to, and that's for me, and that's my major reason for staying in school and trying to read as much as I can and learn as much as I can, and that's what we most of the professor or people who study all the way to the deep level come to understand how weird the whole thing is. So anyway, so that's the deeper level of your rotation and translation. Okay, told you 1,000 times. This is the gist of it. Of course, a general plane of motion, we're going to combine that pure translation and pure rotation. So I don't have to go into it. Of course, this is going to be very complex because you have that and this going on at the same time. So it's just a combination of all your translation and rotation motions. And I just already told you about that. Every real world objects and outside of this world move that way as far as we think they are. Of course, we do have limitation. I mean, we don't know much about the space. We speculate. We only know just a little bit, but we don't even know all of the Earth. But anyway, so this is as much as we know. All right. So let's go on to the next slide. Alright, this is reiterating the pure translation, but here we emphasize that the rigid body is going to move from one point to another, zero rotation. Okay, first we say like pure translation, and there's no rotation. Now we go into it is going to move from point to point, yeah, without any rotation. So going straight line. Yeah, my straight line is very bad in drawing. So anyway, and again go into the rigid body. That's the rigid body, and we're gonna go to each point in the rigid body, and they also move. Okay, they also move on the same path as in the resultant path or the direction. Yeah, and the difference with the pure rotation is they have the same speed, by the way, the resultant speed of that body, and each point also move the same direction with the same speed. Okay, very important, by the way. And of course, if we think about our previous example, is like translation is like your train moving on a straight track, and every part of that train down to the very small particle of that train, okay, is going to move forward without spinning. And if we take another example, let's pick a box, a box being pushed across a table, like a book slide on a table on 2D plane, and that is going to go in a straight line. It won't rotate. Okay, all right, so that's just want to reinforce the previous pure translation, and we go a little bit more details on it. This is just your interactive textbook activity. So here is asking you to draw the paths for the motion of this bar, AB bar, and it's going to move from point 1 to point 2. Your point 1, your point 2 is right here. And it's going to go with pure translation, motion in a straight line. So let's see. Oh yeah, sorry, I forgot to. And of course, we're gonna go. The very first one is for rectilinear, and the other one is a curvilinear. It's on your chapter 2 and chapter 1. Okay, so your drawing should be like this. Translation, go straight line. So you have your AB bar is going to translate from here to this position, point 1, and go to point 2. Okay, so your bar AB is going to remain parallel to its original position, and just go straight from one point to another. And of course, the bar AB is going to move from this position to here. And again, see, there are many points on the AB rigid body. There, you're gonna go with a pure translation. And of course, the very first example is your rectilinear motion. So the bar is going to move in a straight line from one point to another. We can go back to our train example. Train is going to move along the straight train track. Curvilinear, the bar is going to move along a curve. See this part, this path and this path is totally different because this is straight and this one is curved. See, one curve and the second curve right there. So it go like down like that. Okay, so but it still keep its orientation the same to like translate. So example, your car driving along a curved road but not turning. Your car going to drive like this. That's not rotating, that's just translating. But the path, right, the route or the path is curved like this. So pay attention to the path. Curvilinear, curve, but it's still linear. Rectilinear, just straight. Rect mean a rectangle, and just go straight. So your bar AB always remains parallel to its original position. Your bar AB always remain parallel to its original position. Meaning like parallel is not this and this. Okay, parallel mean that and this, by the way. Your rigid body. See? It's remained the same because it's translated. Doesn't matter a straight path or the curved path. It got translated. Why? Because this rigid body, see, stay parallel to each other. This is a parallel, not this. Okay. Make sure you know what you're looking at. Then we will go back into our kinematics. So we will look at velocity and acceleration and kinematics. So we think about all the points in the rigid body. It just Yeah, it just went pure translation. Yeah, and of course each point is gonna have the same velocity. Yeah, and the acceleration. Yeah, so your v, your a is gonna be the same. Yeah, all the points again, even if we go down all the way down to the little tiny point on this AB, yeah, rigid body, each point also have the same velocity. Okay, for translation. So don't forget it. Now we're gonna put what we understood into the mathematical formula, and in there we have velocity. Yeah, velocity of A is equal to the velocity of B. That is just showing you point. Yeah, there are a gazillion point on that AB body, by the way. We're just writing 2 points. Yeah, and the acceleration AB is the same thing. Okay. See, like how it makes you confused, you know? So you got A and B and you're like, what? I don't understand. What is this A and B? That's just point, okay? On the A n and B n, let's just say it. But it's the same thing, yeah? But it said all the points on there maintain the same velocity, and that's what it's saying, okay? Since you have the same velocity, there's no change, yeah? Zero change in velocity, so therefore acceleration is constant. All right, the next one. Then we'll get into the next type of motion this rigid body can do, and that's your pure rotation. Yeah. So pure rotation, your rigid body is going to move in a circular path around a fixed point. So you have your axis. Let's just say this is your body, and it is rotating. Okay, and of course it is this path is, if you draw it, it's just a circular path. Yeah. And it is of course happening at a fixed point because you've got your axis here. Because without this axis, you won't have a rotation. Okay, so this little tiny thing, and this axis is represented by a fixed point like that when you draw on a two-dimensional plane. Okay, so all points on your body is going to rotate through the same angle at the same time. Yeah. Don't forget your velocity of these points are different depending on where that point is from that center. Yeah, but the angle is the same. Yeah, so here another confusion is going to come. So the angle, yeah, it's a little bit difficult for drawing on there. Yeah. So anyway, so the angle is, let's just take it the same for now. Yeah, otherwise you can see it for now. So you have all the points on the body, and these points on that body is going to rotate through the same angle, and it is happening at the same time in the rotation. Okay. All right. The farther a point is from that rotation, let's say this point is far away from the center than this point near to the center. Okay. And when you look at the speed, okay, the speed of that point, yeah, let's just say that's a 0.1, is higher than the point near to the center, right? So the speed of the point far away is higher, yeah, than the speed that is closer to the fixed axis, yeah, which is the fixed point at the center. Yeah, the faster it moves, the farther away from the center. Okay. Example like your ceiling fan, yeah? Previous example, rotating around the center. Your door swinging on its hinges. Your merry-go-round at a playground, yeah? So all of them are the example of your pure rotation. Okay, the merry-go-round going around. So if you sit here, you're gonna experience more velocity than if you sit near to the center. So you have horses outside, and then you've got a cart inside like that. Okay. All right. Then we go all the way down to the different points, move at different speed in rotation. Yes, and like your translation. Your points closer to the center again is going to move slower, and the points farther from the center is going to move faster. Okay, Then we're going to do a little drawing again. So you still have your AB bar from the previous example, and it is going to rotate. And of course, every rotation will rotate about a point or axis, yeah. And let's see how it does. So pure rotation looks like this, and this is a pretty good diagram, yeah. And we have this AB bar, yeah. And that AB bar, you have let's just pick a point A, yeah, moves in a circular path. So see this path is circular path around your point. The center point is now B, yeah. So this is point B, the center of fixed point, and you have your circular path here. Yeah, see that? How nice this is. Of course, you can complete the circle by drawing all the way like this. Mine is not very good circle, but you got the idea. It is a circular path. Yeah. So the object is doing a pure rotation here. Your B is the fixed point because it is at the center of your rotation. Your A here is going on this circular path, yeah. And don't forget, even though we show only two, point to simplify things, you have billions of points on that rod, by the way. And that entire body is going to rotate through that, yeah, same angle, meaning like the angle is right there, okay, through the angle. And it's not very good drawing, but you got the idea of how the rotation angle is that, and every point is going to rotate through that same angle. Yeah? That's a little bit difficult for you to be able to see it right now, but again, your velocity outside is going to be larger than the velocity closer to the center point. So if I just pick a point here and then a point there, the velocity this point is experiencing is going to be slower than the velocity that point is experiencing, because this point is far away from the center. Yeah. So here, of course, we're going a clockwise direction. And don't forget, every rotation has two direction, clockwise and anti-clockwise. Of course, if you put it in three-dimensional space, you can be able to look from three different planes for that motion. And we have 360-degree directions all around. Don't forget that as well. Student in CAT class, they have issue trying to see how the direction changes with their mind. Don't worry about it. It takes some time, but you will get it. Okay. We're gonna cover only 4 sections in your chapter 4. For level 1. So the next section is your fixed axis rotation. Your fixed axis rotation is you are rotating, your rigid body is rotating about a very fixed, doesn't move axis. Alright, then we come back to our second type of motion, which is pure rotation for the rigid body. So pure rotation, again, your review, the body is going to rotate and about a fixed meaning, now it defines what fixed is. It's not moving, fixed, non-moving axis. This axis is not moving. Everything else around it is moving, everything, meaning the points, any points in your body, rigid body, will be moving around it, except the center point. The center point is going to be totally fixed because that's your axis. Meaning like the speed right there is it just there isn't, so when you think about it, speed is large here and then slower and slower as it goes towards the center, and when you get to that middle point right there, there's only one, you can only draw a line on that, and we call that the axis. So all the points, again, don't forget, the point is when they're like that, your line is a set of points. Don't forget that I'm drawing very, very exaggerated so you can see every point in that line. Okay, they're not together, by the way, they're just there with some forces attract to each other and staying there, aggregations. So anyway, there is no permanent bond at all. They're just staying very close, very, very close to each other. And if we translate that into mathematical expression, we call the line as a set of points. So anyway, so each point go all the way towards the center right here, it won't bear any velocity anymore. Velocity is 0, therefore it is fixed, it's not moving. That's what it's saying. Very simple sentence, but it bears very, very deep meaning. So make sure you think with it. Non-moving, therefore there's no translation right there, okay? And every point in the body is going to follow, since it is rotation, it is going to be in a circular path. So even though we draw with this line, if you think about the path, there are so many circular paths for each point it's going around in that rotation. Okay, so we have a resultant path. We usually define with one circular path, and then you have little tiny little point, okay, along that body, the gazillion billions of them, and they are all going in a circular path. Each one of them. So you have many different, like your magnetic lines. Definitely like that. Anyway, so the key point, now we're going to translate that into meaning, into mathematical representation. So let's bring our angles. So here we get the very first angle, theta. So that's your position, because it is showing you where it is from your reference axis. Your x-axis is your reference point. Then it's go all the way about this much angle, you're going to find this rod. So now you go that much of angle, theta, and here is your rod, your rigid body. Okay, so that just showing you the position of that rod is this much angle far away from that reference, which is x-axis. You always have to have a reference point where you start that motion. In this case, is a pure rotation. Okay, so that's where this angular position comes from. So this theta is angle. It is showing the location, so therefore angular position. It's going to measure how much the body has rotated. So this body has rotated, let's say 40 degrees, from OX to here. And then of course we have another angle, which is so that's our position. Every time an object is subjected, by a motion, subjected by a force, and it is in motion, your velocity and your acceleration, they all come in addition to your position. Now in rotation, we are just changing, okay, the symbol from s to theta. So therefore your v velocity is now, we use it with omega, which is this guy. So angular velocity. Then your acceleration is now you offer, so angular acceleration. So that's your position, velocity, and then your acceleration. Position change, you got the velocity. Velocity change, you got your acceleration. So again, little changes mathematically is differentiation going forward direction. And of course your velocity is going to measure how fast that body AB is rotating. And of course your acceleration is going to measure how quickly that rotation speed, which is this guy, is changing. So this guy is depending on how quickly the velocity is changing. The velocity is depending on, okay, how fast that body is rotating. Okay, so you must know this, okay, back and forth in your brain. So example, we're gonna go back to our swing. You can find a pendulum. It's a very good example. A swinging pendulum rotates about is a hinge. It will go ding 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 like that. So here I go up here on the website and show you a swinging pendulum. Okay, so this is just a swinging pendulum, and I can of course let's see if they're gonna move it. They're talking too much. Let's just go a little more and see. Here we go. So that's your swinging pendulum. So you can see the rotation is happening on that rigid body. Okay. Of course, the pendulum, the hinges, here is a hang right there. It's going to go like this, and it is rotating from here to there. So if I go to draw this, it's like this. See your hinges right there, and it's going to rotate like that. Okay, so now you can see the circular path. Alright, so we get back here, And here you can be able to see, mathematically we define everything. Oh, I, write this angle, which is theta, and that's my angular position. So everything in rotation is defined with angular. But that's just position. Your omega is velocity, but we're in rotation, so therefore we use the word angular. And then your alpha is acceleration, but we're in pure rotation, so therefore we use the word angular. That's angular acceleration, angular velocity, and angular position. Okay, and here, of course, this is your circular path. We stretch that out for you here as well. So every particle in that body, there are billions of them, composing that body. Every particle in that body is going to move in a circular path. Even though we show one circular path, there are many. See, it shows one here and one there. See how different the circle's radius, okay, is. So of course at this center of the radius is 0, and your velocity is also 0, and the angle is, there isn't any angle. So about the fixed axis. Then we will go into the angular kinematics relationship. This is very easy. We're just reiterating your angular position, and we stretch the unit, and it's going to be a new unit, and it is called radians. So we say like from here to here is the angle. The angle are in degrees. We note that, but in our case, we're going to use another system, which is called the radians. So this unit theta, we're going to call that angular position in radians. Of course, the radian is going to be abbreviated like that. So radians, this is an English word. When we write the unit, you're going to see red like this, RAD for radians. Okay, and velocity, again, velocity is position divided by time. So therefore, you have your position is radians divided by time is usually in second. So therefore, you get radian per second for angular velocity unit, which is your omega. And then we're going to put that into mathematical position, which is omega is equal to little changes in the position, which is this theta, and the little changes in, and that motion is happening in an interval, which is this guy, on delta t. Little change, little d means it is a little change. If we write it this way with a triangle, it means a little bigger change than that. These are minute changes that we are analyzing. So anyway, so your angular velocity unit, radian per second, formula, right? D theta divided by dt as time. So your velocity, angular velocity, is a vector because it has a distinct direction going that way. So in this case, we're going anti-clockwise. And you got to understand the direction of that. So that's what it's noted here, because the velocity is a vector and is going to direction, towards that direction, which is, in this case, we will define the direction going that way. Okay. All right. So now we are going to get into the direction of that velocity, angular velocity. And mathematically, we define the direction by using I, okay, and then J, of course, and then K. So that is your X, Y, Z. So every axis has two directions, and we are going to use IJK, yes, to define the direction. So for example, your x-axis is gonna have a I plus, and then a plus I and minus I. Your y-axis is gonna have a plus j and minus j. If I take this as a y, plus j and then minus j going this direction. And then your k is going to be your z-axis, plus k and then the minus k. So here that is what it's saying. I am on the z-axis. Let's say this axis is going to be the z-axis. My direction, I'm going to the positive k direction. Now you only have two. Doesn't matter what axis. If this is a z-axis, your direction is k plus, and then k minus. K minus meaning like I am going in the opposite direction, of k. Okay, so minus is, there's no value in it. It's just telling you, hey, I'm going opposite to where you're going. minus means I am negating what you're doing, yeah, contradicting what you're doing. But anyways, the opposite means going 180 degrees to the other side of where you're going. Alright, so example would be like a spinning bicycle wheel. Has angular velocity, which is when you look at the bicycle wheel, it looks like this, right? Bicycle wheel spikes are like that, and there's a fixed, right, center axis is right there. It's going to go right around that fixed center. So you have your angular velocity is going to point outward from the wheel center, yeah. So your direction is going to go that way because your axis is this, yeah. So your k direction is k plus direction is going that way, okay. I think you got it. You need to get this, okay. So some of the people use a little thumb, right? Your thumb is going to point in the direction of your angular velocity. So you will call your fingers in the direction of the rotation, yeah. So if you call your finger in the direction of the rotation, your thumb is going to go, okay, the angular velocity direction. Your thumb is going to point in the direction of your angular velocity. So it's like this. Your thumb is going to point like this, and your fingers you're curling that way, okay. See, you're going motion. You're going to call your fingers in the direction of that motion. Your motion is going that way. So therefore, yeah, this thumb is pointing in the direction of your omega, okay, your x. Sometimes some students are getting reverse of that. Just be very careful. Also, there are many misconceptions in YouTube channels. Some people are trying to make, and they also have it a reverse. Just be careful. If you don't want to draw any of it, the best way to try to understand is go with the axis, okay, and just make sure that you locate the axis, yeah. So as soon as you locate the axis, you get the direction, yeah. Very easy because your axis is a line and it has only two directions on it. You can make one positive and the other one opposite of that positive is negative, yeah. And we do the same thing for angular acceleration. Since it is acceleration, we're looking at the change in velocity, so therefore your unit is radian per second square, yeah, like your meter per second square, yeah. Now radian is referring your position. This is from previous chapter. Now we're in rotation, that's translation. So we're in rotation, so therefore our unit is radians divided by second square for angular acceleration, and the formula, we're going to use a little change in the angular velocity divided by a little change in t, which is your time, yeah. Your direction again is going to go, yes, along your thumb, where your motion is along your fingers, and here is going to be the positive z-axis, which is a k hat, yeah. Then we will get into velocity and acceleration of a point. We have already stressed, yeah, so in the rotation, your velocity is going to increase, yeah, from the fixed axis. So if this is your fixed axis, your velocity at this point is higher than the velocity at that point, okay. Of course, we're assuming this rigid body is tied with the road to the x-axis. No, that's not a very good example, but you get the idea because your circular path is going to be like this. So the velocity, yeah, far away from the fixed axis or fixed point here is going to be higher than the velocity that is closer to the fixed point. So the farther a point is from the axis of rotation, the faster it moves. Yeah, in common word that we say. Of course, here the same thing, yeah, see, like how this is gonna go that way, yeah. So if we put it in a formal sentence, your velocity increases as a distance from the fixed axis increases. Suppose that's your fixed axis and this is your body, yeah? And the farther away the point is, it's going to have a higher velocity. So your jump road is a little bit difficult for you to be able to see because the handles is going to move slowly, yeah, closer to the center. The middle of that road, which is this guy, yeah, is going to move faster. This is a little bit difficult for you to be able to see it, yeah. And this one is easier for you to see, yeah. So the foot is going to move slowly because it has a smaller radius, yeah, and the ball is going to move fast because it has a larger, yeah, radius. This is your conceptual example 4.2, yeah, 1, and I'm just giving you the answer, yeah, how to look at it. So here the question is saying like, what is the velocity direction of any point on a rigid body undergoing pure rotation? So you look at it tangent to its path of motion. So the is talking about your pure rotation, and then every pure rotation is happening on a rigid body, and we already analyzing the point on that body, yeah. So it's asking you what is the velocity direction of any point, yeah. So we want to know the velocity direction of any point. One is the velocity tangent, the direction of the velocity tangent to its path of motion, yes. Okay, perpendicular to the line drawn from the fixed axis to the point in question. And then of course it's also, yeah, give you et and then e theta, and that's just angular, yeah, angular position, and this is your time. So you know that this too, okay, is correct right away. It is because this is one example where your direction, okay, they change the axis, yeah. So your z-axis is actually this way, yeah. So therefore, see like how difficult it is for you to be able to reverse it. And this is the one example I'm telling you, which a lot of the textbook and even professors, yeah, they get the z-axis, yeah, reverse, yeah. So anyways, but it is okay because either way, yeah, either way you can be able to make this velocity direction, yeah. The velocity direction depends on what axis you're looking at, yeah. To me it looks like they're not using the x-axis, yeah, even though they write the k, because they're taking that direction, see, that direction as a velocity direction and the reverse of that as a motion direction. And this is what I'm trying to teach you, how when you pick the axis, you know, one of them, x, y, z, you're gonna have an issue because you have no idea like which axis that the person is taking. Especially it happens like this, yeah. So I normally take this as a z-axis, yeah. Some, you know, they now take this as a y-axis and this as a z-axis, yeah. So therefore your velocity thumb and the fingers is going to reverse, yeah. So instead of finger going that way, finger is going this way and the thumb is going that way, okay. It's difficult for you to be able to see it, so make sure that you use your hand and trying to understand that. So anyway, in this example, the author make it, you know, the axis is your z-axis is like that, straight up, yeah, poking out like this actually, and your motion direction is going that way, so your thumb is gonna go this way, yeah. So anyway, so the velocity direction of the velocity is going to be tangent and rectangle, okay, rectangle here, which is your 90-degree, yeah, to that fixed axis. So you can see it's perpendicular to the line drawn from the fixed axis to the point in question. So our point is right here, and this is our circular path and tangent to the path of that motion, yeah. So they're saying like the direction of this angular velocity is going this way, okay. So that's where your thumb is, so therefore your motion, yeah, the rotation motion, your fingers are pointing outside of the page. See like how it got reversed. I usually, but again, like when you define the problem, you can say, you know, I'm taking this as a z-axis and point your finger out like the previous example that I just showed you. To me, I get it easier if I put the z-axis that way instead of poking out like that. Okay, so that's up to you. This et and e theta is just a one unit, vector. So that's a tangential unit vector. And I said it time. Sorry about it because I didn't, know like what this textbook is referring to, and they shouldn't put this in it. You're not at that level, but it's okay. This is just showing you e for the unit vector and t. They meant it not the time here for this textbook. It's actually it is a tangent. It meant for the tangent. It's a very bad way of writing. So anyways, the et, the tangential unit vector, and e theta is going to be the radial, normal unit vector. Even I got wrong, So because of the way that they write this position, they should never take this position and t as a tangent. So anyway, so this is your tangent unit vector, and that is a radial normal unit vector. Is just so this is going to go toward the center of the rotation, and that is going to go along the direction of the motion, which is tangent. So A and E is pretty much the same meaning, and B and D is pretty much the same meaning, But of course, the way that they wrote it, even I got confused, right? So the answer is all of them. You would definitely choose A and B, but then you have no idea because of the way the author used the symbol. I would say not very good. Okay. The next example is also from your interactive textbook. So we're going to use the arc length equation we will use this, that equation, and then we're going to derive the velocity of a point A, and our rigid body is AB, this rod, and that rod is going on pure rotation. Again, don't forget the X, all right, the axis that using is the axis is definitely poking out of the page, okay? And then of course they're going, thumb direction is in this direction, tangent to the path and perpendicular to this axis they're taking. So your motion direction is poking out of the page, and your velocity direction is going that way. Of course, we're going to start with the arc length equation, so therefore we are going to start with our ds, and then r, and then d theta. So that is just little change in position, okay? And then of course this is also little change in angle, which is angles meaning angular position, and that is a linear position, okay? And our aim is to derive a velocity at that point. This point can be anywhere, okay? We're just putting it there, so you can see it a little bit clearer. I can take that point here too. It's the same thing, So the arc length equation is this one, ds equal to r, which is your radius, and then d, okay, theta. So let's look at it very carefully what they mean, because the symbol can be defined by the author, whatever. So we gotta understand like what is it that this author is trying to say. So ds is actually here, see? So we're just, this is meaning like change in position, ds means little change in position going from this, your point 1, and that's your final point 2, going from here and then go rotation, right? That much of angle difference. See? So, and we know that the angle, your origin is this 0 or O origin, OX is your reference, okay, axis that we measure the angle from. So from here all the way to here is that. So from there to there is this little angle, and that is the change. Meaning like I move from here to here, I rotated from this point to that point, rotate that much of angle, and we call that the delta, okay, theta, which is a change in angular position, this much change, and of course your ds is this little one, okay? That's a translation, I would say like a regular position, position 1 go to 2, which is, you can put it in a line. We usually put it 1 point to another point 1, point 2, and then your location S1, S2, so the change in your position is ds, only for that line. This is angular, and that is just the regular position, and we are connecting that two, yes, and because this is your arc length, is the length change from that point to this. Arc mean your arc, okay? So your circle is like this, and your arc is like this, yeah. So now the length of that arc is only curve, right? We call it a curve path, so we can still use a regular position change for that, yeah. So you know that that's a regular, and that is the arc length, okay. And this is your angle, which is your angular position changes. All right. And of course, this r is your axis, yes? The distance of that point from the fixed point is RA, yes? So we know this, and that. Angle, the path length, only that section, and then the distance of that point from the fixed center, all right? So that's what you're seeing. Okay, then we will continue. So here we continue to derivation. Derive means this is we're doing derivation here. So we will put, all right, time, yeah. So we're gonna to put the time because everything is happening, yeah. Activities. So one activity happened, and then later that activity is like this. So we call it from here to here is a, you know, whatever that event happened, and we call that time, you know, measurement. And the activity one happened like this. Later, the activity, you know, another activity happened to the same object, and we have a point interval from here, the first point to the end point, and we call that the time because we're measuring the activities, you know, in the space. So we put the time factor into it and start taking the derivation, yeah. Derivation means we're going towards the forward direction from position to velocity, yeah? So we're at this location right now. So position, and of course we're trying to get the how to get the magnitude of the velocity. So we put the time factor into it. If you put it on this side, of course you have to balance the other side by putting the same thing. So you can cancel it and we will still be the same, yeah? So now we put that in. So now ds by dt is velocity, regular velocity, yeah? And d theta by dt is your angular velocity, yeah? Of course, this is your distance of that point away from the origin, which is your fixed point here, yeah? So now we have derived the velocity of point A of that rigid body, yeah? Your dr by dt is going to be 0, yeah, because dr represents this, yeah? So therefore this the change, okay, the change in that distance from here to here will always be 0 because your rod, you know, doesn't change in length. So the distance from here to here, even if it is subjected to this interval, you know, that we're analyzing the activity that happened in that interval, this distance will not change because it is the same rod, you know, and the point won't move right there. Okay, I'm going to stop here, yeah, and then we are going to get into the rotation about a fixed axis for velocity, okay, in the next video. It's too long, so I'm going to try to break it into 1 hour long, yeah.